Hello, my name is Paul Blowers, and today I'm presenting work that we've done at the University of Arizona entitled Application of Quantum Chemistry to Evaluate Radiative Forcing for Emerging Class of Atmospheric Pollutants. I know it looks like a really long title, but basically we want to tell a story about a compound that was discovered in the atmosphere above Canada by researchers about 3-4 years ago, and how this class of compounds is now emerging, showing up in industrial use, and what the implications might mean for global climate change. Again, my name is Paul Blowers. This is work that I did with Sebastian Galaski, Buba Diallo, Benham Safavinia, Marissa Gonzalez, and Ryan Petronella. You can see him way up here climbing in the mountains just north of Tucson. So this is work we've done over the last year or so, and the context is environmental hindsight is always 20/20. We as humans have done a lot of different things in our human history, and we find out that they weren't very good ideas. So, for instance, DDT destroyed the bird populations. It was introduced as a pesticide, and it took us about 30 years to figure that out. Methyl butyl ether was introduced as an oxygenator for gasoline, and California and the United States implemented it and required it as a gasoline additive. And it turns out that every tank that we make as humans tends to leak, and then this compound is soluble in water. So we replaced tetraethyl lead in gasoline, which was toxic, with something that was even worse and now was water soluble. So we had to go back and kind of collect all the MTBE and not use it in that way. We introduced the chlorofluorocarbons, which were awesome refrigerants and solvents, and they were great. But 30 years after we introduced those, 40 years, we discovered they cause ozone depletion. Fluorocarbons have been discovered to create or contribute to global warming, and the hydrofluorocarbons as well. So our question is, can we predict some environmental behaviors before these actually get out in widespread use? That's the question. What other chemicals will we find out are not acceptable? That's our burning question. Basically, we want to generate the data that will allow informed decision making by policymakers. So instead of introducing a compound and then banning it and trying to collect it, we don't do that in the first place. I'm going to set the stage and talk about greenhouse gases. Essentially, the Earth collects sunlight all day, and it radiates infrared energy back out from the Earth's surface into the troposphere. And it does that 24/7. So we have this infrared energy that's being radiated away from Earth, and if we happen to have a compound up here in the troposphere that has frequencies that line up with the infrared intensity of that energy leaving Earth, that molecule now captures that energy. GWP is defined as the integral from 0 to some time horizon, and I'll come back and I'll define that, of the radiative forcing AI, which is what this work is really all about, and then this concentration dependence as a function of time. You normally assume a charge of the compound gets out at time 0, and then it reacts away exponentially. And so when you multiply the radiative forcing times that concentration and you integrate it over the time horizon, that gives you the absolute global warming potential. And when you divide it by the reference compound, CO2 data, you get the relative GWP with respect to CO2. The time horizon here is typically chosen to be 20, 100, or 500 years. And I like to make a joke. 20 years because the politicians are about 50 and they're not going to be around after that. 100 years because they might actually have kids, and 500 years if they actually care about the environment. So just a little joke that on why those fall into those categories. So if I wanted to get GWP, what I have to do is I have to have a very sensitive spectroscopic method of obtaining really highly accurate IR energies. So I get the IR frequency and the intensity of those peaks, and I transform that into the absorption cross-section. I send the absorption cross-section off to modelers at University of Illinois, where Wubbles has done the work, and he can then tell you what the radiative forcing after running this on a supercomputer. I need to know the rate constant of removal from the atmosphere if I want to get this concentration profile as a function of time and get that exponential decay, and just using primary chemical engineering reactor design equations. We have to have some reference compound data, and if I have these two pieces, I can get the atmospheric lifetime, which replaces this equation, makes it a little bit easier. And then I need the reference compound data. So we have all this, and what we're trying to do is get this radiative forcing. So radiative forcing defined is having this absorption cross-section and then putting it into these bins of wavelengths so that we can then figure out what energy is captured that normally would not. And so here this orange line is called the percent transmittance of the current atmosphere that we have above Earth in the troposphere. And we see that about 650, all intensities of IR are already captured by water and other compounds that are present. However, we have this atmospheric window here where when we put a compound out that has peaks in this area, now we're going to capture the energy that would have normally escaped out into space. So we see that this compound here has a bunch of peaks in this atmospheric window, and every one of these is going to capture energy that normally would escape. This method was developed by Pinnock. Papasava and coworkers found a way of doing this from quantum chemistry, and what we did is we refined it a little bit, and we made these bins that Pinnock had smaller, so we have a higher resolution result. I'm going to switch and now talk kind of in the context of where the perfluorocarbons that we're going to talk about fit in regarding the United Nations Environmental Program. So new classes of compounds in the United States are being introduced constantly. We do not have the doctrine that Japan and Europe have, which is do no harm. Instead, in the United States, companies can introduce chemicals until we find out they are harmful. So slightly different depending upon which country you're living in, but perfluorotributylamine has been introduced, and it's used as a heat transfer fluid in transformers. It's used as a blood oxygenating agent, and it was discovered over Canada, and they followed where the wind had come from, so it's coming from these very sparsely populated areas and more intensely populated areas, so it has sources all over, so it's not just one point source located somewhere. And in that work, Wallington and coworkers reported the radiative forcing value to be 0.86. And that led to a global warming potential of 7,100. I had done some prior work. Oh, I want to back up. The UNEP classifies PFCs as strictly CF compounds. If you throw an amine in there, now it's not covered by the United Nations Environmental Program regulations regarding perfluorocarbons. Even though it is a perfluorocarbon, the amine makes it a different class. So these will not be covered by emerging regulations. Why do we care? Well, it turns out that these have been introduced as ultrasonic imaging system agents, as matrix materials for encapsulation of pancreatic cells, as a whole blood substitute, as a oxygenation delivery mechanism, which is interesting. I'll come back and I'll talk about that near the end. And as a support for hydrogen-oxygen separation from electrolysis, if you wanted to get pure hydrogen. So it has lots of different uses for these different compounds. When I saw the value of 0.86 a couple years ago when the paper came out, I knew based on my work with hydrofluoroethers that the 0.86 seemed really low to me. What we had done is for about 35 different compounds, we had predicted the radiative forcing values. So the predicted radiative forcing is on the y-axis. The experimental radiative forcing is on the x-axis. And we want the prediction to equal the experiment right here on the 45-degree line. We want to be right there. Well, it turns out that the two best experimentalists who might obtain a radiative forcing are going to be plus or minus about 25%. So if I'm within these two bounds, then I've done a really good job predicting. If you see a range along the x-axis, like this line or this box, it means that two experimentalists measured the value and they got within that range. If you see a range in the vertical direction, that means that there were two or more conformers where we could compute different shapes of the molecule and get different radiative forcings. And so that's why we end up there. And you see that about 95% of them were right in that range of best prediction. For this work, what we did is we justified having to do the quantum chemistry by taking all our prior hydrofluoroether data, and I know it's a different class of compounds, but we just wanted a gross approximation. Hydrofluoroether data of radiative forcing, and we plotted that versus the number of carbon-fluorine bonds. And if we do that, we would predict with this very crude model, very, very crude, that NF3 would have a radiative forcing value of 0.25. It really has 0.21. And our model would suggest that this PFTBA, this perfluorotributylamine, would actually have a radiative forcing about double the prior one. So this is why we wanted to get in and do the quantum chemistry. So what we did is we chose the B3LYP6-31G star level and method in order to calculate our frequencies and geometries. We assumed there are no symmetries. We then checked, and all these compounds that we're going to share data on all had positive frequencies. So there's what the optimized trimethyl perfluorotrimethylamine looks like, the ethyl, the propyl, and the butyl. And so let's look at what our radiative forcing values AI come out to be when we use that binning method that Papa Zava had developed and that we had proved extensively worked very well for hydrofluoroethers. We see that we are within 0.2% of the predicted value or the experimental value for NF3. The prior only other perfluoroamine compound radiative forcing that was published was from that study from Canada. Actually, they weren't in Canada, but it was out of the US. And they reported 0.86, and we calculate 1.23. So it's not as bad as it looked according to our crude model, but it's still 50% higher than the past experimental value. We did the methyl, ethyl, and propyl as well, and these have never been reported, so this is the first time that these have ever been reported anywhere in the literature or in presentation form. And we see that these do go up dramatically with the more fluorines that you put on, as we expected. So again, just comparing those values. This justifies that we do a good job at this. So did our prior hydrofluoroether work, and this shows what we expect the new value to be. The GWP of this compound is reported to be 7,100, and so we went ahead and we computed the 220, the 100, and the 500-year global warming potentials. We get 9,550. Again, in context, what this means is I can emit 9.55 tons of CO2 or 1 kilogram of this compound, and it will contribute to global warming the same. In this context, HFC-134A is a refrigerant solvent, and it has a GWP of 1,320, and the US EPA has just banned this compound from being used in mobile air conditioning systems. And its GWP is 1/9 of even the best of these. So should we ban the perfluorocarbons? Not if there's nothing that can replace it in industry, but we should certainly start looking for alternatives. Or we should make sure that we can capture 100% of it. So here's an implication. The reason that you need to charge up someone who has very severely injured lungs. Basically what you do is you infuse the lungs with this fluid, you completely fill it, it delivers oxygen, but it protects the tissue. Every time you exhale, some of this is going to get exhaled. You're not going to be able to capture that. So these are almost designed for release into the atmosphere. Current concentration of PFTBA is only 0.15 parts per trillion by volume, but these other compounds are going to get in the troposphere and contribute to global warming as well. I'd like to thank you for your time. A whole body of people who helped support the development of this, including my colleagues that helped in the most recent past. If you have any questions, don't hesitate to email me at blowers@email.arizona.edu. And I hope you're having a good day or evening wherever you are.